Respected Chairman, Honorable Chief Guest, respected dignitaries, respected Director Sir, faculty members, and my student friends, a very good morning to one and all. I am Vinny Somaya, and I feel privileged to welcome you all today on behalf of Dr. V.N. Bedekar Institute of Management Studies to today's session, History of Mathematics. On behalf of Dr. V.N. Brims, I welcome our today's chief guest, Dr. Clemency Montelle. A huge round of applause for her. With a huge round of applause, may I please invite Dr. Montelle to take the charge.
Thank you so much for inviting me here. This is actually my second visit to the Thane campus and the first of many to Mumbai. Basically, I'm trained as a mathematician, but what my research expertise is looking at the history of mathematics. And of course, India, just because it's such a wonderful country, filled with so many amazing people and such a long history, in comparison to my own country, New Zealand, which is only about 700 years old in terms of the human population, and of course a quarter of Mumbai's size. So India is a really important source of research inspiration for me. So I'm delighted to come and talk to you about some of the absolute jewels that are here in the culture regarding the history of mathematics. So thank you very much for inviting me here to talk today. So I'm not used to talking to business management students, but I'm assuming that probably all of you have one of these, or at least one of these textbooks on your desk as you pursue your studies in business management and related fields. But I would hope that in a business management textbook, I didn't have time to pick one up, that of course there's a chapter, at least one chapter dedicated to mathematics. Of course, everybody needs mathematics, from somebody who's building a table, a carpenter, to somebody who's fixing your plumbing, to somebody who's building bridges or buildings, to management students. Mathematics is ubiquitous. Mathematics is omnipresent in everything we do. And thus, when we look at some of the earliest civilizations in the world, of course we find mathematics. It's absolutely essential for human activity. Whether it's sophisticated or not, mathematics is omnipresent. So part of mathematics, of course, that was incredibly useful and still remains very useful today, but in slightly different contexts, is, you can see it's just cut off here, trigonometry. Does everybody have a little bit of trigonometry background in some of the maths course? Yes, okay, good. Some of those maths questions in your papers that have trigonometry always tend to frighten students. There's nice little sine and cosine and tangent functions, of course, which are very simple, but find themselves in all sorts of incredibly complicated mathematical contexts, as well as very simple ones. Now, the beautiful thing about trigonometry that is so omnipresent today in absolutely everything you do is that we find that its origins were in fact in India. So it's one of the things you can be justly proud of as a culture, is some of your ancestors brought to light trigonometry and the trigonometric functions that we use today. So we see here, this might be your average page, maybe in the back of your book about trigonometry. You can see, of course, we have this triangle with the hypotenuse, the adjacent. We have our sine theta, cos theta. We have this circle with our various trigonometric identities. And I've pulled this out of a manuscript which is about 300 years old. And of course, you can see we have a circle here. We have some various triangles, even if you can't read the Sanskrit. But you can see that indeed there's very close parallels towards measuring our triangles on our circle, and indeed the various relations between different sized triangles and the like. So I'm going to take us all the way back to the beginning of the history of trigonometry, which emerged on the Indian subcontinent, and ask questions like, who needed trigonometry? Why was it invented by mathematicians? What did they use it for? How did they understand it? What did it look like in the particular maths textbooks? Because what we will find is, despite the fact that trigonometry is absolutely essential for mathematics today, back then it had some very different features than it does today. But some things haven't changed at all. So that's the beauty of history of mathematics. So before we go back to trigonometry, I just want to focus on three very interesting things about mathematics as it was practiced in early Indian times. Three things. A lot of the time we compare our mathematical tradition with other ancient cultures, such as ancient Greece or the Romans or early history of China. Mathematics to us seems something that's, well, it's mathematics, it's the same no matter who does it, it's a very global subject. But what we find as we go back in history, mathematics gets done under some very different circumstances and looks very different. If you pick up a Chinese mathematical textbook that's 1,000 years ago, it's very different to a mathematical textbook that we might find in India or in some other civilization. So mathematics can actually be different depending on the people who are doing it. So I want to pull out three interesting features of mathematics as it was practiced in India in early times that really makes it quite a remarkable tradition. So these three things are the number of written documents, the ideal of oral learning, so I'll look at all of these in turn, and the tradition of the commentary. Now, absolutely phenomenally, and here's some numbers for the management students, there are estimates, and this is probably on the high side, but of course big numbers are what we like, that there are probably around 30 million manuscripts extant in India today. Now what's very interesting about this number, more conservative estimates might say there are around about more like 7 or 8 or 10. It's still a staggering number. It surpasses the amount of manuscripts that's available in any other single culture in the entire world. So in terms of having source material, India really wins the prize for the number of manuscripts. What is also staggering about this number 30 million, or between 10 and 30 million, that's a big gap I know, is that because of the climate conditions here, and because of the source in which these manuscripts were written on, paper and other things, most of these are no more than about 300 years old because they just disintegrate. They just don't last. So this 30 million actually only represents the last 300 years. If the paper had lasted, if we actually had every single document that was ever written, this would be compoundly as high. So in terms of the resources, Indian intellectuals were absolutely incredibly industrious in terms of producing the source material. This is just a fraction of what actually would have existed in the entire corpus. Now, depending on what you want to call science, of course, sometimes we call it in management studies management science. So science is a very broad word. And in ancient times, it defined things such as astronomy, mathematics, some astrology, panchanga making, all of the stuff, metalwork, even cooking, some people would put in science. But depending on what we really want to define as scientific, and of course this is really back of the napkin type approximation, maybe about 10% of these are scientific. So we're talking about 3 million scientific manuscripts for which to paint a picture of what was science like in the history of India. So a lot of these are still sitting in various manuscript repositories across the country. And I just take one here. This is actually from the University of Madras. And this photo doesn't quite show, there's this lovely juxtaposition. And this is sort of my soapbox of look after your past. This is the manuscript library here, which is seemingly undergoing endless renovations. But in the background here, you can't quite see it, but there's beautiful, glossy, brand new law building. So it's sort of an indicative of, what's important to put money into these days. But nonetheless, it is a beautiful collection and pretty well looked after despite this juxtaposition. So this is the manuscript, government oriental manuscript libraries, and these are all over India. So if you're traveling and you want a tourist thing to do, go check out your local manuscript library. I mean, it truly is like going into a beautiful novel or something. And there are just rows and rows. Ambushed by the odour of camphor, which is a natural pesticide. You know, this is second knowledge to all of you, a natural pesticide to make sure that the manuscripts don't get eaten, literally, by small insects. Another way to look after them is just to brush them, a very fine toothbrush to keep the insects off them. So there's all the sort of the fact that we're dealing with physical artifacts from which to understand some intellectual history of India. So it all starts here. This is the sources that we have. Some of them are well organized. Sometimes manuscript libraries just become overwhelmed by this 30 million number of manuscripts, but with recent digital technologies, it's becoming ever more easy for people just to put things in a scanner and scan them and make them freely available. And of course the scholars are just ever so happy to get their hands on these manuscripts and read them. And here's one here, very small, you can see. This hole in the middle is a form of book binding or manuscript binding, which would keep the pages in order. And this is a form of Tamil script here, which looks rather scary to me, as I'm sure it does to some of you as well. So there they are, very well preserved manuscript, the direct insight that we have into India's past. So that's point number one. India has an enormous amount of sources from which to understand your history from. The second thing, which is somewhat at odds with the number of written documents, is the veneration of the oral tradition in this country, which is something that is so incredibly admirable as well. That is, in very early times and still even today, that is many texts that were written in early times, the Vedas, Upanishads and other texts, were meant to be committed to memory. And so you have remarkable feats of memory of people being able to remember hundreds and thousands of verses and being able to chant them off. So despite the fact people were writing things down, part of the epitome of intellectual achievement was to memorize intellectual content and to be able to speak it out at will orally. So there's this lovely juxtaposition between writing things down and committing things to memory. Now, what happens when you need to remember a whole lot of stuff? You remember the management textbook that I had. If I said to you, okay, I want you to memorize your entire management studies textbook or entire mathematical textbook, you'd probably look at me and just, you know, think, this is just absolutely impossible. You know, how do I remember something that says, you know, a textbook? You know, it's 100 pages. You know, it's not very interesting. It's not even interesting when I don't have to memorize it sometimes. So what happens when you have to memorize a whole lot of stuff is some very interesting things happen to the content. First of all, you chuck out all the stuff that's not necessary, right? Okay, if it's not necessary, we're not going to spend time trying to memorize it. Secondly, what we find is that intellectual content, including mathematics, gets cast in the form of beautiful verses with a metrical pattern, so it's memorable. So some of you will have remembered sutras or shlokas with various wisdom that, you know, your parents might have told you. And it's in a metrical pattern. It's almost like a song, so it's easy to remember and cast at will. So what we find is that all of the mathematics that we see in early time was composed in the form of a poem. And students would remember this poem, and because of this, they would be able to memorize huge amounts of material and bring it back at will. So every theorem you can think of, mathematical theorem, important numbers, were composed in the form of a metrically definite pattern, and we'll have a look at some of these at the moment, in a minute. Of course, the minute that you, so is this still working okay? The minute that you put things in a poetic format, some very interesting things happen to the content. That is, stuff which is only slightly relevant tends to get dropped out, okay? In the interest of being short, because your brains have a limited capacity to remember things, you might drop things out. If you can write things down, you can put whatever you like. You know, you can write your book as long as you want. The other thing that we find is that, which is particularly interesting in science, is there's no fixed technical vocabulary, because if you need to fit things in a poetic meter, you need many synonyms, so you can find one that fits into the syllables you have available to you. And we'll look at these in a minute. The other thing, which is a big contention among mathematicians who look at history, particularly in the advent of Ramanujan, who composed these amazing books and said, I'm just too busy, I have all these amazing ideas, but I don't have time to prove things. And of course, he's left his legacy for many of the brilliant minds of the 21st century to prove, is that you don't really put a mathematical proof in a poem, right? It's mathematical proofs, you know, are very meticulous, they're very precise. You can't really put them in a poem like you can just a result. So this is of contention. Of course, many scholars say, okay, well, Indian mathematicians didn't feel it necessary to prove everything, therefore their mathematical tradition isn't very sophisticated. This is a failure of those historians to understand the context in which these were carried out. So let's just have a look at some of this mathematical poetry in action. So I'm sure most of you don't read Sanskrit, so I haven't bothered putting in Devanagari up. But I'm just going to show you an example of one of these verses. Actually, we'll do this one second. We'll do this one second. We'll do this one first. So of course, mathematics, just like management studies and science, has a lot of numbers in it. And some of these numbers are really important to remember. So here's an example. I'm just going to recite this poem. You'll just see some of the flow and the meter will help you. You know, you'll probably end up chanting with me. It's sort of so ineluctable to try and join in. So this is a verse which in Sanskrit, which goes Vibuddha netra gajahi hutashana triguna veda bhavarana bhavaha. Okay? So it's a nice little ditty. You see there's a real rhythm that's taking you along and helping you to remember. Now, if we go through very carefully the Sanskrit, Vibuddha in Sanskrit means gods. And this is a very poetic way. Of course, now that we all have cell phones, nobody can even remember anybody's phone number anymore. But apparently, psychologists tell us our human mind can remember about 7 digits before the numbers just become meaningless to us. So remembering a big long number isn't very memorable. So instead, what scholars would do would be to choose objects that by everyday or religious significance could be associated with a number, and they would use that instead of the actual number. So Vibuddha, traditionally, which is the Sanskrit word for gods, means 33, there being 33 million gods. Netra, you see that's next, this is a lovely big compound, Sanskrit loves making compounds, means eyes. So eyes, of course, reminds us of the number 2, all right? Gaja, elephants in traditional mythology. Actually, does anybody know why there are 8 elephants? I've never been able to figure this out. Anybody know a story? You know, I have my own stories from my English tradition, but there are 7 dwarves, there are 3 little pigs, there are 3 blind mice, all of these folklore, but I've never known why there are 8 elephants. Somebody knows, they can tell me in the question session. There are also 8 snakes. Ahi means snakes. Hutashana is fires, the 3 eternal fires that burn. So Vibuddha netra gajahi hutashana. So we have this very long number. So you start at the very end. So we've got our 33 here, our netra here, which are eyes, our elephants, our snakes, our fires, and so on. So remembering this very long number here, we're in this very compelling verse that goes, God's eyes, elephants, snakes. Okay, you can kind of, if you went out of this room and you said, oh, what did Dr. Montelle speak about? You think, oh, she had this verse, it was about God's eyes, elephants. So it's memorable. You'd probably never remember this number by itself, okay? And so forth and so on. 3 is the lovely word for 3. Guna are qualities of 3. Veda, there are 4 of the Vedas. Ba are constellations. Again, we've got a different word for elephants now. So you can see this interesting varied vocabulary for the same thing, which drives mathematicians a little bit crazy. Mathematicians are a little bit precise. They like having one word for one concept, but of course when you're composing it in verse, you need synonyms so you can fit it into the poetic meter and arms. Okay, so we've got this very long number. What's the point, you all may say, okay? This verse that reads God's eyes, elephants, and the rest of it. Well, the verse continues, the wise said that this is the measure of the circumference when the diameter of the circle is 900 billion. Anybody have an idea what this number might be? Impress all the eminent people in the front row here. Anybody have any idea? Give you a clue. Talking about a circumference and a diameter. Yeah. Yeah, close. Earth's circumference. Yeah. What has a circumference and a diameter? A circle. What are some of the very important numbers related to a circle? Pi. Good on you. Okay. Fantastic. Excellent. I'm proud management students have such great mathematical skills. So literally, if you grab out your very long calculators here, you take this number, which you can remember by God's eyes, elephants, snakes, etc. You divide it by 900 billion, and you will get pi, 3.141, exactly precise to 11 decimal places. Okay? So in the form of a poem, something that's memorable. In fact, you could learn this yourselves. So if you're in the test and you've forgotten your calculator, you need pi. You could use it even in modern days today. Okay? But can anybody have a clue as to why, this is very early on, this is, the first millennium in Sanskrit, why we might have had to memorize this very long number and not just 3.141, etc., etc.? Any ideas? This is kind of a harder question. This is in the time before decimal points, okay? So it is that early. So rather than multiply it by 3.141, they just multiplied by this very long number and divided by 900 billion, okay? And they would get this very accurate approximation for pi. So in the form of a beautiful verse that you can commit to memory just by taking 10 seconds or so, you have remembered pi to 11 decimal places. So that is the form of mathematical poetry, and that is one of the features that Sanskrit mathematics, or mathematics in India, is so famous for. This is quite a simple example, but they would encode almost everything in verse. Let's just go back to one other example for an example of this mathematical poetry in action. So we have this other verse here, which is in Sanskrit, and it reads Karanakirtihe kotikirtim vishodyamulam bujo bajasya kirtim, etc., etc. And it's in a different metrical pattern to the other one. Now, if you do a direct mathematical translation of this, we notice that subtracting, so here's what it says, subtracting the square of the base from the square of the hypotenuse, the square root is the upright. Anybody got any ideas what this rule is about? Excellent, fantastic. Does this verse tell us that it's a rule about a right-angled triangle? No. It says we just discard that material. We don't have enough room in the verse. Once you start understanding the rule, you'll absolutely know it's the right-angled triangle theorem, which incidentally was used by ancient Indian scholars as early as the 8th century BCE in the form of the Shilpa Sutras. So way predating Pythagoras, we see this in India, but this is quite a later thing. So the square of the base from the square root of the hypotenuse, the square root is the upright. What we notice, though, is when we read the next sentence, subtracting the square of the upright, the square is the base. Now, these dots are mine. This is because we don't have enough room in the verse to put this little dot here. What we need, subtracting the square of the uproot from the square of the hypotenuse in here, the square is the base. The author has left that out because he thinks all of my readers are intelligent enough to put that information in there themselves. So this is what sometimes composing mathematics in a technical and a poetic environment entails, that some of the content has to be dropped out because there's just not enough syllables to include it. But the intelligent reader can supply what they need by context. So of course, as you absolutely see in the last phrase, the square root of the sum of the squares of the base and the upright is the hypotenuse. And so you see 3 different ways to express Pythagoras' theorem, okay? That's because this is the time before algebra. We really see this as being sort of one concept and we only need to remember it once. But for those early people before algebra, this in a sense, Pythagoras' theorem was in a sense 3 different rules or 3 different variations on the same rule, which they would remember again in the form of this beautiful verse. So this is another feature of Indian mathematics that some of you may or may not be familiar with. The last feature that we'll look at is the commentary. And this is because sometimes the verses are composed in such a beautiful fashion and are a little bit ambiguous, or they're so poetic that we need somebody to tell us what's going on. And later people came along and wrote big long commentaries to explain the content in a very erudite way, and they would do so over pages. So sometimes even the smallest verse here, so all the stuff that's in slight bold is the base verse, and all the rest of it is the commentary. Okay, just to tell you how much information these early scholars could encode in just a few syllables, which would then be unpacked by later scholars. So without the commentary, I'm lost as a historian for what's going on in many cases. Sometimes the context is not enough to figure out what's going on. Okay. So let's go back to looking at an episode from the history of mathematics. Back to trigonometry. Now that you're familiar with some of the features of Indian mathematics, let's actually have a look at some more. So, what we want to look at is some trigonometry. So sine theta is something that you probably see on a daily basis. But where did it come from? Okay, very interestingly, you find sines, of course, in mathematics textbook and management textbooks and all sorts of places, but the very earliest forms of sine that we see are not in mathematics textbooks. They're in astronomy textbooks of very early time. So that tells us something about where the motivation to develop these trigonometric functions came from. So we look at astronomical textbooks. So what do we mean when we talk about the sine? In fact, you use it so often that probably it's lost its meaning in a geometrical context. But what we're talking about when we talk about the sine is if you imagine the circle again, and you've got some arc. We ask the question, given an arc of a circle, what is this straight line here? And that's all it comes down to. So given an arc on a big circle, what is the chord or the perpendicular that we can drop down from that circle? And of course, this is important for very early people because it helps us discover what the height of something is in the sky. Okay, if you imagine your sky, your stars are on this big backdrop of this fixed circle. It helps us identify the height of a mountain and all sorts of things like this. So given this arc here, what is the chord? Now, very early treatments of circle geometry, such as that was developed in Greece, actually looked at taking the chord of an entire arc. But actually, these sorts of triangles are kind of annoying to deal with mathematically. What we need, what mathematicians much prefer, is right-angled triangles, right? They're really easy to do things with. We can apply Pythagoras. So the insight that Indian mathematicians made was, let's take half of this triangle, okay, and then we find a right-angled triangle which has many more mathematical properties, and we'll call that length there the sine. So we take half the arc of double the chord, okay? So that amount there is the sine for this given arc here. And that allows us to do a lot more trigonometrically. Now, some of you will remember watching, of course, The Hobbit and Lord of the Rings, right? It's something that New Zealand is quite famous for, and I'm probably going to get mileage from this slide for about another 5 years before the next generation will have been watching something else. But still, here we have our favourite character in the Lord of the Rings. What's his name again? Legolas, exactly. The beautiful elf with the amazing blonde hair. Anyway, noted for spending most of the movies going around with this incredible bow and arrow and shooting orcs at face value. Okay? So, Middle-earth, we see bows and arrows, a lot of them, and of course, what I can do is superimpose, and I'm not just doing this as a joke, I have an actual academic reason for doing this, is that if you imagine our bow and our string and our arrow, and we draw a circle around them, we can actually see some beautiful mathematical symmetry in here. So you can imagine we see the arc is our bow, as our actual bow. Our bowstring, which is being pulled back here by Legolas here, okay, goes into the middle of the circle, or down here when it's left taut, when he's not shooting orcs, okay? And then we have our arrow along here, which is also another important component. Now, I'm bringing a little bit of New Zealand or Middle Earth to the stage, but of course you have no shortage of amazing stories of warriors in India with bows and arrows. They're all around you, be it with Arjuna or Kama with his bows and arrows. You see it in beautiful sculptures around the cities, all around India, and artwork, and fill in your mythological narratives. So bows and arrows are absolutely big in India, and we know that given the terminology that Sanskrit authors used for the sign, that they must have been inspired by this bow and arrow picture. So, for instance, just remember the bow and the arrow here. The word that Sanskrit mathematicians used for arc was chapa, which literally means bow. So they were visualizing this in their mind. When they looked at a sign, they saw a bow and arrow. The sign was this bowstring here, and the arrow along here, or shara in Sanskrit, was this thing called the verse sign, which we'll look at in a minute. So Indian mathematicians were inspired probably by the bow and arrow to give their names to the trigonometric concepts. What's even more remarkable is something that we call a bow and arrow and a bowstring came directly to our English tradition in quite remarkable linguistic way. And because I absolutely love words, and I love words that are going through different languages, ja or jiva means our bow or our sign. Okay, they're two lovely Sanskrit words. Arabic scholars who travelled to India to learn about their amazing mathematical secrets, or sharing technology as we might call it today, took the word jiva as well as the trigonometric concept, and they said, this is a brand new concept in the Arabic language, and we don't even have a word from it because we don't even have trigonometry yet. So what are we going to call it? So what they did is they took the Sanskrit word and they transliterated it. That means letter for letter, they gave the equivalent letter in Arabic and used that as their word. So the J became, so this is al-jaib here, the J became the J, the long I here became this long I here. And in Arabic, you don't have a V sound. The closest thing that they have is a B sound. So the V became the B. Now, funnily enough, al-jaib in Arabic already exists as a word. Okay, it means a bay which ships sail into, or a gulf, or a stream. So it already exists in the Arabic language. But so they just had two meanings. I mean, we have a lot of instances of words in all languages which can mean at least two different things. So al-jaib means a bay or a gulf. Now, the Latin West scholars travelled to the Islamic Empire. And they said, oh, what's this very interesting thing that you can measure arcs and their lengths given the circle? So Latin scholars looked at algebra and they said, we don't have trigonometry yet. We need a word for this. And they said to the Arabic scholars, what does algebra actually mean? And they said it means a bay, a gulf, or a stream. The word in Latin for a bay or a gulf or the stream is sinus, okay? So they translated algebra for sinus, from which we get sine. So we can go in a linguistic way directly from sinus back to algebra, back to algebra. There is a direct legacy from the Sanskrit jiva to sine, and it's an absolutely beautiful linguistic transmission from one word to another, which all can be explained what jiva and sinus have in common, okay? So that is absolutely beautiful. So from India right to modern times via linguistics. Okay. So let's have a look at how this sine table manifested itself. How did they remember signs? How did they use them in their work? Okay, so what we're going to do is say, so we're looking for this. Given this arc here, we want to know what is this length here. That's the question that scholars wanted to know. And so we all know about sines. We only need to learn the first quadrant because all the other quadrants are equal by symmetry, okay? Most of your sine tables, of course, only go up to 90 because of the lovely symmetry of sine. So scholars were asking, if I vary this angle, if this line goes up and up and up, what is the length of this? That's the basic question they were interested in asking. and they looked for different amounts of theta. They gave different amounts of this. And this is on a circle which had a radius of various sides. If I asked you, what is the sine of 90 degrees, what are you going to say? 1. Okay, so we in modern times imagine that our circle has a radius of 1. But in early times, again, because of this lack of the decimal point, they had various radiuses. Some were up in the thousands, some were 150, 120, 60. So all of these were scaled, if you like, depending on what size of the circle that you made. So they had various values of sine. And of course, as you can imagine, they encoded these in the form of a beautiful verse which they were to memorize. And here's one that they were memorizing some sine values. Now it goes, Trim shat, sanavara sendu, jinatiti vishaya. Okay? That is the sine table. So just with all those syllables, you can remember all the sines you ever need from 0 to 90 degrees. So in other words, Trim shat, sanavara sendu, jinatiti vishaya. We're just going to look at these. So read it with me, just so you can have some time to do some mathematical poetry yourself. Okay, ready, go. Trim shat, sanavara sendu. Lovely. Jinatiti vishaya. Okay, so what does it mean? Trimshat, okay, so just like we saw the encoding of pi with using the verse, how did it go, Vibhuda? Netra, gods, eyes, elephants, snakes, etc. See if you can remember that one at the end of this talk. This too is just numbers, okay? Any ideas what trimshat might mean? 30. Perfect. Sa is a little word in Sanskrit that means plus. So we've got 30 plus. Nava, 9. Okay, so 30 plus 9, 39. Rasa. In Sanskrit, that means tastes. What number?
9 rasas.
There are 9 rasas, but this is a different rasa. Tastes, we have 6 of them. 6. So this is the number taste. So we've got 39, 36, and Indu. Does anybody want to know what Indu means in Sanskrit? Moon. Very good. Indu is moon. How many moons do we have? 1, at least as long as we're not on Jupiter. Right, so we have 1. So 39, 36, and 31. All right, so here are 3 numbers. Repeat after me. Trim shat, sanavara sendu, Jinna titi vishaya. Okay, Jinna. Jain tradition, there are 24 Jain saints. So Jinna is the number 24. Titi. Anybody know how many titties there are? 15. You're really good. See, you thought you knew no Sanskrit. You know a lot of Sanskrit. Vishaya. Yeah, so there's 5 of these. Yep. Okay. So this literally means 30 increased by 9, 6 and 1, and 24, 15 and 5 are the sign differences. Remember that word jya that we had, signs there. There they are there. So these are not signs themselves, but they're sign differences. So I'm just going to put them up here. And they say they're for arcs of 15-degree intervals. So when our theta is 15, we have a sign difference of 39. For 30, we have a sign difference of 36, and so forth and so on. So I can just, because these are differences, of course, the first one will be 39. The second one, I can add these together. So I can just use a little reverse engineering, and I can add in my actual signs. So you see 39 and 36 gives 75, again plus 31 gives 106, up to sine of 90, which is 150, okay? So that's like saying sine of 90 is 1, but here my radius of my circle is 150. So for those of you that are confused and say that doesn't look like my sines, all you have to do is divide all of these numbers by 150, and they will agree with the numbers that you get on your calculator when you type in the sine function in degrees. Okay, so this, in fact, in just a matter of syllables, is a sine table for all of the sines from 0 to 90 degrees. Who's feeling very brave and thinks they can remember the trim shat sanavara sendu titi, jinna titi vishaya? Who reckons they've got a great memory? Anybody? I was talking to an audience of 400 earlier this week, and 1 person could remember the whole thing. Anybody brave enough? Let's just go through once more, because then you will have learnt your sine table. You won't need your calculator anymore. Let's say it once more, and then somebody's going to be brave enough, I know, to... Okay, 1, 2, 3, go. Trimshat sanavara sendu jinatiti vishaya. Okay, anybody brave enough? Put your hand up to recite it. We'll help you in the audience. Anybody want to volunteer one of their friends? Okay, I'll ask somebody at the end. Trimshat sanavara sendu jinatiti vishaya. So you can see how easy it is to remember things when you remember titties and jinas and rasas and the like. Okay, so just to look at a little bit how these signs were derived. Where did they get them from? Okay, how did they understand them? How did they compute them? So the verse tells us what the signs are. The verse does not tell us how they were computed, and that's what I spend almost all my time doing as a research scholar, is given a result that I can read in a beautiful verse, I ask the questions, how did these guys come up with this interesting material? Science, of course, we have a good idea, but when the mathematics gets much more complicated, understanding the brilliance behind the minds that devised these formulas and rules is much, much harder. Sometimes, of course, and this is where the commentary comes in, we have scholars that can give us a little bit of insight into how this was done, including one scholar who wrote on this verse, which was by Brahmagupta, by the way. Some of you will have heard of Brahmagupta, who was working in the 7th century of the Common Era. So this sign table that you've just learned, that you're all busy memorizing now, is at least a millennia and a half old. So we're talking 1,500 years ago. So how did they get these signs? And this is what our commentary tells us. What you are to do, and this is sort of the experimental side of mathematics, if you like, is you to go out so we can understand something of how mathematics was practiced. You don't grab your computer or your piece of paper or your pen. You go on the ground and you make it flat using water. And then you inscribe a circle with a compass measured in digits equal to the radius, and you mark it with 12 points. So here they are here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so we're just following the instructions. Now we take a sutra, or a string, and the commentary tells us, take your string and attach it to two tips of this, and you will form a triangle. Now, can somebody identify what sort of triangle this is? Not isosceles, but close. What's the other important one? Equilateral triangle. Absolutely. And the reason is, of course, if I join up every second bit, your mathematics is excellent, you guys. It's fantastic. Then I'll get a hexagon, and we know about hexagons. The length of the sides are equilateral triangles that are inscribed in the circle. Okay. So we've got ourselves a triangle. Now, if you remember our bow and arrow diagram, you'll have to kind of turn your head to one side. You can see that, given this arc here, this will be the sign that we're looking for here. And of course, for this triangle, we've got an equilateral triangle. This is 60 degrees. So our angle here will be 15, half of that. Okay, so the commentary continues. Half of the string split by the north-south line or split by the east-west line is the sine of one sine, okay? So in other words, we can find the sine of 30 degrees, and it's half the radius here, just by the simple identity of this equilateral triangle. So we'll just write this here very quickly, so we can see how we got this. So if we've got our theta, and you see they're not deriving them in the order that was done. So sine of 30 gives us 75 degrees. And we get that because of the properties of equilateral triangles. What about the next one? Now, the nice thing about a triangle with 30 degrees is we know if it's right-angled, and here's why the innovation of dealing with right-angled triangles is so much nicer, is that we have a 60-degree angle here, and we can find equally the sine of 60 degrees. So if we know the length of the radius, we know this side here, we can use Pythagoras to find the length of this one, and that's the sine of 60 degrees. So this is how somebody 1,500 years ago was understanding how to build their sine table. 130. Okay, so that's about the most mileage we've got out of that triangle. What about some more triangles in the circle to get some more sines? The next important triangle that we have here, which we can do in the circle, remember we're asking, for this arc, what is this length? Is this 45-degree triangle? Now, who can tell me what this triangle is called? This is an isosceles triangle, yep, okay. These two lengths are the same because these two angles are the same. They'll both be 45 degrees. So we can just simply use Pythagoras again to get this length here, which gives us 106. Remember, our radius of our circle is 150, unlike the one that we've found today. So our sine of 45 degrees is 106. Okay, and we can continue onwards. Again, we can write now. This is the last triangle we'll need to get all the other sines that we have here. We go back to our 30-degree triangles here, and we can draw another triangle. Now, this one, which has the red line as its base, is also an isosceles triangle, okay, because it cuts the chord. And using this fact and Pythagoras, we can find the sine of 15 degrees, which if our radius is 150, is 39. And likewise, we can find that, and of course the sine of 90 is 150. And of course, going through and summing up the differences, remember the verse, trim shat, sanavarasendu, etc. Oh, good one. Gives us our sine differences. And that is how somebody, 1,500 years ago, Brahmagupta more precisely, built up a sine table with just using some very simple circle geometry there. The reason as to why the differences were put in a verse instead of the actual signs themselves might be able to be explained by the fact that there are actually less digits here than in the signs themselves. So this is the idea of parsimony. If you're going to have to memorize it, make sure it's the most parsimonious or the shortest bit of information that you have to memorize there. So there's your 30 trimshat, sanava, rasendu, jina, titi, vishaya there. And that is your sine table. Now the question remains, what say you want a sine which is not one of these angles? Of course, you're used to in your test papers and in your computations, maybe you need the sine of 40, or the sine of 85, or the sine of 10. Simple linear interpolation, that is just taking proportional differences, could be used to find the sine of something in between. So that is one of the most proudest contributions, I think, to the history of mathematics, which has been so enduring that India has shown today. And other scholars, just to finish off now, experimented with various sine values, such as Aryabhatta, who some of you will have heard of, maybe in reference to one of the famous satellite that India put into space, had a sine table, and he had a whopping 3,438 at his radius. And his sine table was a little harder to memorize than Brahmagupta's. It had 24 values. Okay, but again, the same idea applies. A nice little verse composed in the form of poetry to give you these sine differences so you can memorize it and use the numerical data to your heart's content. Yeah. Other scholars came along and thought they could do bigger and better, and this is how the history of mathematics proceeds. Brahmagupta gives you 6 values, Aryabhatta gives you 24 values. Along came Nityananda in the 17th century and gives you 5,400 values of sine. So he gives you the sines down to a single minute. Now, I not only feel sorry, so this is just one page of the sine table. Of course, you know, now with Excel, where you can auto-generate numbers just at the hit of the button, having a big spreadsheet doesn't scare anybody in this room. What scares me about this is the first page out of 12 pages Somebody sat down and copied all of these out. In fact, this is in a manuscript which is 559 pages long of numerical data like this. Not only did somebody have to hand copy out all these values of sines, somebody had to compute the same algorithm 5,400 times to give the answer. So really a real feat of mathematical brilliance and computation. Trigonometry allowed, of course, absolutely obsolete now because we can get computers to do it for us so much faster and quicker and at the push of the button. But really, some of the manuscript documentations really give us a sense of what it was to be a mathematician in India and how incredibly brilliant and detailed they were when they looked at trigonometry. So I'll bring this to a close now. I hope now you've learned something a little bit about the tradition of the history of mathematics in India, some of the context in which it was carried out, and the form of poetry in which it was preserved, as well as being on the manuscripts, which I hope next time when you go to a new city or a new place, you go and check out some of the manuscripts as well. Thank you very much. Now, I'm very happy to take any questions as well. Yeah.
I request the dignitaries to kindly come on the stage.
Okay, if you have some questions.
Yeah. Does anybody have any questions, or is anybody feeling brave enough to recite Trimshat? Yes.
I might be wrong in this thinking. Jiva was translated as Ajiva, which means gulf or a bay.
Yeah.
By geographic definition of gulf of a bay,
Yeah.
is any water body surrounded by three sides. Is this a coincidence or a purpose?
So I really like the creative thinking that's gone into there. I think the linguistic evidence for meaning the same thing rather than the geographic configuration is perhaps a little more compelling, but I do like your explanation and may have been part of the reason behind it. Yeah, very interesting thought. Of course, some bays are more triangular than others, of course, but an interesting thought, yeah. Thank you. Yeah.
Can you tell us something about Vedic mathematics?
Vedic mathematics, do you mean the mathematics that's taught today in schools? Yeah. So unlike its name, this is quite a recent development of which, because it's less historical than some of the very early things that I study, I don't know as much about. But what I will say is that it really reflects some of the points I was trying to get across about this incredible capacity for the Indian mind that has this tradition of doing things in their head and having these incredibly clever approximations and algorithms that they can perform very, very quickly for these numerical algorithms. So in terms of, it doesn't reflect anything that was done in Vedic times, but it's more indicative, I think, of the general culture in which mathematics is practiced in India. Yeah. Any other questions?
Did any of the scientists earlier postulate cos theta, tan theta, or it came out?
Okay, that's a very interesting question. So I've talked a lot about sine. The question was, okay, I've talked about sine, but what about cosine and tangent? So the sine was recognized, and also the verse sine, something that we don't use today. It's quite an archaic concept in trigonometry. That was called the bow. I'll just go back to this slide here to show you it. Where is it? So the verse sine, which is equivalent to the cos, is just this little bit here. Okay? The sine is this, but the cosine is this line here. The cosine was often seen as the complement of the sine. Sometimes it had its own word, but typically it would be understood in terms of the sine. The tangent is an extremely interesting one because it's not so apparent on this diagram, you know, where's the tan? Tangent, in fact, was understood in a very different context under chaya. Chaya is the Sanskrit word for shadow. So if you're trying to ask the question or answer the question, what time is it? before the time of wristwatches or sophisticated timekeeping devices, you would stick a gnomon or a stick in the ground and you would measure the shadow, all of you have seen sundials I'm sure, that the sun cast on the ground. And that is directly proportional to the tangent, because we know the height of the gnomon or the opposite, and we know the shadow length because we can measure it. So we've got the opposite and the adjacent, and we can find the height of the sun, the altitude of the sun, which gives us the time. Time is, of course, how high the sun in the sky is. When it's late in the evening, of course, the sun is very low. When it's about noon, the sun is very high. So the tangent always remained restricted to this one context, and it took Arabic scholars to bring it into the trigonometric concepts. But it was always there in Sanskrit, but it was understood as a shadow and not as one of the three functions that we associate today with trigonometry, sine, cos, and tan. So just because we see it today as a group doesn't mean that it was natural for early thinkers to see it as the same group. So it's a very excellent question. Yep. Fantastic. Okay.
Trimsha Sanavara Vendu Jinatithi Vishaya. So this is a phrase that most of us would remember for a long time, and mathematics is so interesting and so fun to learn. This is what Dr. Montelle has taught us today. Thank you so much, ma'am. On behalf of Dr. V.N. Brims and everyone present here, I would once again thank Dr. Montelle for her precious insights on history of mathematics. I would kindly request our chairman, sir, to present a token of appreciation to our chief guest for today.
Thank you.
Thank you, sir. Thank you, ma'am. Now, may I please request our chairman, sir, to share his few thoughts in today's session.
Well, friends, we all are convinced now that the history of mathematics is very important from Indian point of view. Madam, I can just, because my mathematics was very poor, so I went to B group, that's medicine. Anyway, the history of mathematics is quite interesting, and what I see, other than pure mathematical text, it has evolved out of many other areas, simple observation of the nature. And I see that from the history point of view, whether you see the Syrian monk in the 6th or 7th century, or Leonardo in the 12th century, they have talked about Indian traders, those who have gone there in the Middle East or they have gone in the Africa, and from them they have learned what these numbers are. I think a lot of work will have to be done for Indian tradition of trade also, because they have carried those numbers and so many other things there. Well, friends, it's a very interesting topic. There are a couple of things she has explained, from how it has been preserved through poetry, and the most important thing is to preserve our manuscripts. She talked about 30 million. I can tell you it's more than 50 million now. And at Thane, at Institute for Oriental Study Thane, we have more than 3,000 manuscripts preserved there. Somebody like you youngsters will have to come there and study them. And this work is going on. You can understand, if she can do that in New Zealand, why not we here in India? She talked about Bakshali manuscript. I can tell you that on net I can request all our heads. There is an exhibition going on in Science Museum of London on 5,000 years of scientific achievement of India. It's in a science museum. And I was there a couple of weeks back, and I have made a PPT presentation on that. And in that there is a Bakshali manuscript kept there. You can see that actually, that manuscript there. So I would request all of you, I have passed it on to the heads, and they can pass on those PPTs to all students, and they can see many things there. Well, friends, with this few words, I request all of you, it is not difficult. I can tell you one thing. Most of you understand Marathi. Sorry, madam, I'll talk something in Marathi. you know, things percolate to the common sense and common language. In Marathi, there is one phrase we talk, Gunya Govindani Nanda. You understand? Sakani Sukhani Bhandu Naka, Gunya Govindani Nanda. Now, if I tell you if that's mathematics, you will be shocked. गुण्या हा तुम्हाला माहिती आहे, तुमच्या नसेल. आमच्या वेळे कंपास बॉक्स असायचा आणि त्याच्यामध्ये गुण्या असायचा. यू विल अंडरस्टँड व्हॉट दिस गोविंदा इज. अगेन यू हॅव टू गो बॅक टू द हिस्ट्री. दोज डेज, दोज मेसन्स अँड अदर थिंग्स, ते ओळंबा टाकायचे वर्ण, आणि ओळंबा टाकून तो काटकोनामध्ये किंवा त्याच्यात आलं तर दे यूज टू से गोविंदा झाला. अँड वन ऑफ द फिल्म्स ऑल्सो ही सेज गोविंदा वॉज अ बजवर्ड यूज for some secret message to be passed. Govinda Jhala means exactly it has come, it has aligned. And that's how it came in Marathi phrase, Gunya Govindani Nanda. Unfortunately, this has not been taught to you in your schools. You have been asked questions, but the teachers have not explained you what do you mean by Gunya Govinda. And now I can tell you, we have found out at least a dozen phrases in Marathi like that. They are actually mathematical explanations. Find them out. That's a work given to you. With this few introductory or few remarks, this is quite interesting. I would request Dr. Joshi to conduct such lateral lectures for management students, and I'm sure they would enrich you, they would inspire you, and you will look more deep into our history. Thank you. Thank you very much.